Okay, this is problem number 15, which if you remember the hints, turns out to be fairly simple. It's not actually a case of integration by parts. So every time that you see a product of two functions, it doesn't necessarily mean it's integration by parts. First thing you want to do is to check whether it's U substitution. And so in this case, we would let U equal the exponent of e to the x cubed. Therefore, the derivative of u du would be equal to 3x squared dx. We can see that we have x squared dx. So what we would do is we would rewrite the original integral as 1/3 the integral of 3x squared e to the x cubed dx. So that's going to be du, and this is going to be u, so we can make the substitution. So this integral becomes 1/3 the integral of e to the u du, which is a basic integration rule. So we integrate that, and we get 1/3 e to the u plus our arbitrary constant. Now, because we're dealing with indefinite integrals, we have to substitute back in. So we get 1/3 e to the u. U is x cubed. So that's the solution to this problem. It didn't require integration by parts. So don't always assume just because it's in the integration by parts section that it is integration by parts. Okay, we're going to do problem number 16, which is integration by parts. Because there is no u substitution that's going to work here, so we have to go to the next thing. We have a product of two types of terms. We have a polynomial and a natural log, which are typical type combinations. So we want to decide which one we're going to call u and which part we're going to call dv. And the rules are that if we have a simple integral, we'll call that dv. So we don't know what the natural integral of the natural log is. There's no simple integral. But x to the 4th dx does have a simple integral. It's just a polynomial power rule type integration. So what we'll do is we write this down. So we're going to say u is going to be the natural log of x, and dv will be equal to x to the 4th dx. And when we take the derivative of the natural log, it will be a simpler function. So the derivative of the natural log is 1 over x times dx. To get v, we integrate x to the 4th dx, which will be x to the 5th over 5. And we don't have any dx or anything there. Okay, so those are the 4 parts that we need to do integration by parts. And the formula for integration by parts says if we have an original integral where we can identify u and dv separately that work out correctly, it's equal to u times v minus the integral of v du. So we have u, natural log of x, v is x to the 5th over 5, and then we integrate v, which is x to the 5th divided by 5, times du, which is 1 over x dx. So these are the parts, u, v minus the integral of v du. And the idea is that this integral will be something that we can integrate, whereas this one we couldn't integrate directly. So let's just simplify things. We'll take the first term and we'll put the constants in the polynomial out front. And what we have here is the x to the 5th divided by x is x to the 4th divided by 5 dx. So this is just a polynomial again. So if we integrate that, we're going to get well, let's factor out 1/5. That's this 1 over 5. And then we have the integral of x to the 4th dx, which is just x to the 5th over 5 again. And this is the point where we add the arbitrary constant. So to the final answer, we just need to simplify the second term by combining the two constants. 5 times 5 is 25. So we're going to end up with x to the 5th over 25. And actually, I can see just a little bit more we can do, which is we can factor out x to the 5th over 5 or 25, I guess either way. Let's factor out x to the 5th over 25. And what that does is we have to put 5 times the natural log of x here, and we have to put -1 there. It's just a little cleaner because you've got a common factors. We could have done x to the 5th over 5 times natural log of x minus 1/5. This way, we just have everything as whole numbers. Problem 18, section 8.2. So we're going to use integration by parts on this equation, which is 1 divided by x times the natural log of x cubed. Actually, I'm not sure whether we're using integration by parts or not. I'm just looking at this because the first thing you want to do is you want to see whether you can solve it just using normal integration techniques, using U substitution. So there is a possibility this would work out with U substitution, which I think it does now that I'm just looking at it again. So what we would do is we would let U equal the natural log of x. And so therefore du is 1 over x. The derivative of the natural log of x is 1 over x, and we multiply by dx. So you can see we have dx over x. Therefore, the equation can be written as du, which is dx over x, divided by u cubed. And then we do the integral, which of course is the integral of u to the minus 3 du, being a polynomial now. We can then add 1 to the exponent, which becomes u to the -2 divided by -2. And so we can now move that back to the denominator. Once you do the integration, you can move it back to the denominator. So we would have -1 over 2u squared. And then we could substitute back in u, which was the natural log. So we end up with -1 over 2 times the natural log of x, quantity squared, and I should have added c here, my arbitrary constant, plus c. So that is the answer. But just to be 100% sure, I'm going to check the answer book. And we are in section 8.2. Problem number 18. Oh, wrong section. So we get -2 over the natural log of x quantity squared plus c. Okay, so we're in good shape. This is problem 20, section 8.2, calculus. If you've just watched 18, you've seen where, or my original thought was it was integration by parts, but then I looked at it. Now this one, you would think, okay, well, what if I let u equal the natural log of x, then du would be equal to 1 over x. and therefore maybe that would work, but I have 1 over x squared. So, and if I chose u to be x squared, there's nothing that even resembles natural log of x in this case. So this is a good opportunity to use integration by parts. And so we look at it and we say, okay, what are we going to call u, and what are we going to call dv? Usually, if there is the natural log, that is going to be u, because there is no simple integral of the natural log of x dx. So that makes it usually pretty easy if it's an integration by parts problem. So we're going to let u equal the natural log of x. Therefore, dv is what's left over, which would be dx over x squared, which of course is the same as not negative. It's going to be the same as x to the negative 2 dx. So then we take the derivative of u, which is 1 over x times dx. The integral of x to the minus 2 power dx is going to be equal to x to the minus 1 power divided by negative 1, which is the same as negative 1 over x. Okay, so the next thing we do is we write out the equation for integration by parts, which says the integration of u dv is equal to u times v minus the integral of v du. And then we plug in. So we have u, which is the natural log of x, times v, which is negative 1 over x, minus the integral of v, which is negative 1 over x, times du, which is 1 over x dx. And once we clean that up, let's move this to the front. So we'll have negative the natural log of x over x. Negative times negative is positive, so we'll put a positive sign there. The integral of 1 over x squared dx. And so we say, okay, is this something that we can integrate using a simple rule? Well, we just used it right up here, so the answer, of course, is yes. So we do the integral, and since we've already done it, there's no point in redoing it. So we would be at negative 1 over x, and this is the point where we add the arbitrary constant. So that was problem number 20, and that answer is correct. Problem 25, section 8.2. So this one's not as obvious because, in terms of integration by parts, because, you know, these are both, there's no sines or cosines or natural logarithms. But again, using the philosophy of u is usually the derivative, which is simpler than the original function. So if I take the derivative of x, I get 1, which is definitely simpler. If I take the derivative of this, I'll get 1 over 1/2 times 1 over the square root of x minus 1, which is at best the same and probably a little more complicated. So because of that, I would choose u to be x and dv to be equal to the square root of 1 minus x dx. Okay, so dv is x minus 1 to the 1/2 power dx, and du is dx, 1 times dx. So now we integrate this to get v. So the integral of that, what you'll get is you'll get x minus 1 to the 3/2 power divided by 3/2. So we add 1 to the exponent, and we divide by the new exponent. So v is going to be 2/3 x minus 1 to the 3/2. And this, you know, the level of complexity is not as critical here because we're not looking to reduce the level of complexity. We're trying to find the most complicated function that we have a simple integral for, which is in this case true. So let me add another page. So we have u, du, v, and dv. So we write the integration by parts equation, which says that u, integral of u dv, is equal to uv minus the integral of v du. And then we substitute. So we have u is x, v is 2/3 x minus 1 to the 3/2 power. Then we subtract off of v, which is 2/3 x minus 1 to the 3/2 times du, which is dx. So what this allows us to do is to integrate that, because that is another simple integral. So I've changed the order on the first one. And the second one, you're going to have the constant, negative 2/3. And then we have the integral of this. Well, it's basically the same as the integral here, except we add one more. So we get x minus 1 to the 5/2. 3/2 plus 1 is 5/2. And we divide by the new exponent, 5/2. And we add our arbitrary constant c. So the final answer is just going to be, as we kind of clean this up, and we actually did this integral before. This is where, so we'll talk about that in just a second. Let's multiply this out. So dividing by 5/2 is like multiplying by 2/5. So we're going to get negative 4/6, which is 2/3. So let's just go ahead and, no, 4/15. 2 times 2 is 4, 3 times 5 is 15. Times x minus 1 to the 5/2 power plus c. Okay, now, this was back in chapter 4, I think it was, when we were looking at using u substitution. And so I'm just going to do this down here. What we would have done is we would have said u is equal to x minus 1, du was equal to dx, and then you solve this one for x. So x is equal to u plus 1. So you take all those and then you substitute it in. So for x you put u plus 1. For u, x minus 1, you put u, so you get the square root of u, and for dx you put in du, and we did that integration, and you can see we're going to get u to the 3/2 power here, and when you integrate it, get u to the 5/2, and when you get u, square root of u times du, you integrate it, you get u to the 3/2 power. So that's where that all works out, and it may look like this is kind of a different format, but it is the same thing. So I just want to point that out. So let me just check here before we log off here. Make sure I got this right. 3/2 x minus 1. Yes, you can factor out an x minus 1 to the 3/2 and a 2/15, and you can rewrite it. So let's just go ahead and do that. So if we factor out 2/15 times x minus 1 to the 3/2 power, what that leaves is you would have 5 up here, 5x, because you have the x remaining, and if you take 5 divided by 15, you get 1/3. And then you would have here, we'd still have 2 left over, so we'd have minus 2. I think that's what it is. No, actually you have minus 2 times x minus 1, because x minus 1 to the 3/2 times x minus 1 to the first power is x minus 1 to the 5/2 power. And then you simplify inside the last bracket. So we'd have 5x minus 2x, which would be 3x, and you'd have negative 2 times negative 1, which would be positive 2. And so that's the other form of the equation. This is problem 31, section 8.2. Okay, this is another integration by parts example. We have the variable t. We're doing this in terms of t instead of x, but it's still variable. And we've got this product of cosecant, cotangent, and hopefully we'd say, oh, I remember that. That's something, so I'm going to go to page 520 and see what it is. So I'm turning to 520, and I see that cosecant, cotangent has a simple integral, which is the cosecant. So that makes this decision pretty easy because the derivative of this would actually be fairly complicated. You have a product of the cosecant and cotangent, and it would get very long. So, and also the derivative of t is simpler than just t. So both of those make the solution, the selection of u and dv to be pretty easy. So we're going to let u equal t, and we're going to let dv equal the cosecant of t, cotangent of t, dt. So this is u dv. We take the derivative of t, and that's just dt. We integrate v, and we look on page 520, and it's negative the cosecant of t. So the integral of cosecant cotangent dt is negative cosecant t. We don't put the arbitrary constant in there. We write the integration by parts formula. U integral of u dv is u times v minus the integral of v du. We plug the things in, so what we'll get is t times the negative the cosecant of t, u times v, minus the integral of v, which is negative the cosecant of t times dt. So this is v du. Okay, now hopefully there's an integral for the cosecant, and there is. So we'll put negative t cosecant of t, just putting a negative sign out front. We'll end up with a positive sign. And the integral of the cosecant of t, we look in, again, page 520, and we see the integral of the cosecant of u du is negative the cosecant of u plus the cotangent of u. So in this case, u is t, and so what we get is we get negative the natural log of the absolute value of the cosecant of t plus the cotangent of t. And then we have to add our arbitrary constant at this point in the integration. So we just add c to the end. And the other thing we have to fix is this negative sign. Just get rid of this extra parentheses, which is not really needed. So we get negative t cosecant of t minus the natural logarithm of the absolute value of the cosecant of t plus the cotangent of t plus c. So that was problem number, what we're working on here, problem 31, and we're good. Okay, we're on problem 50, section 8.2. So this again is a good problem for integration by parts because we have x, which when we take the derivative of x, we get a simpler term. The sign, we have an integration for the sign. So we can go ahead and make those substitutions. U is equal to x. dv is equal to the sine of 2x dx. So du is just dx. And the integral of the sine of 2x dx is going to be, okay, so we could use u substitution, but we have u here, so we could use w substitution. So what we know is that we somehow have to reflect this 2. And what happens is when we integrate it, we have to multiply by 2 to get 2 dx, because if we take the derivative of the sine of 2x, we get the cosine. Well, if we take the derivative of 2x, we get 2 dx. So we need 2 dx, so we'd have to divide by half and multiply by 2. So we get a half in front here. So you get 1/2, and also we have to take into account the integral of the sine is negative the cosine. So v in this case is going to be negative the cosine of 2x divided by 2. Okay, now we write the integration by parts formula. The integral of u dv is uv minus the integral of v du. We plug in, and we get x times u, which is negative the cosine of 2x divided by 2, minus the integral of v, which is negative cosine of 2x over 2 times dx. This is v, this is du. So v times du. So the first part is negative x, cosine of 2x, the whole thing divided by 2. Now here we have the integral of the cosine of 2x. Well, we did the same kind of thing here, the integral of the sine of 2x. So the factor of 2 is going to come into play again. So let's go ahead and negative times negative is positive. Let's factor out the 1/2. So what we'll have left is the integral of the cosine of 2x dx, which is going to be equal to 1/2 times sine of 2x. It's positive because the integral of the cosine is positive sine. If you go to page 520, look that up. So we'll get 1/2 times the sine of 2x and then we add our arbitrary constant to everything else. So the final answer, once we clean everything up, is we get x. Well, this actually is the I forgot that we have to do the definite integral here, so we'll have plus 1/4 sine of 2x. So rather than my arbitrary constant, I should have, let's go back over here. What we're looking at is the integral from 0 to pi, so I'm going to put this all in brackets and integrate that from x equals 0 to x equals pi. And likewise, this will also be integrated from x equals 0 to x equals pi. So now we just have to evaluate these at the upper and lower limits. So let's go ahead and do that. And what I'm going to do is I'm going to evaluate this at the upper limit and subtract it at the lower limit. So I'm going to, we'll have negative pi times the cosine of 2 pi divided by 2, so that's the upper limit. We subtract it at the lower limit, which will be 0 times the cosine of 0 divided by 2, which of course is going to be 0. And then we have plus 1/4 times the sine of 2 times pi, which is evaluating at the upper limit, minus 1/4 times the sine of 2 times 0, and that'll be the sine of 0, which is 0. So every term, the sine of 2 pi is also 0, and this is 0. So the only thing we have left is this part. And the cosine of 2 pi is the same as the cosine of 0, which is 1. So we should end up with negative pi over 2. And so this is problem 50, and that is correct. Okay, so that's the right answer. So again, what we did is we let u equal x, dv equal the sine of 2x dx. We integrated dv to get v, which gave us negative cosine of 2x over 2. We plugged that into the equation, and then we integrated the cosine of 2x dx, which was equal to 1/4. I guess that's on the bottom of this page, or on the top of this page. So we had 1/2 from here, negative positive 1/2, and then we integrated, we got 1/2 sine of 2x. And then we evaluated it at the upper limit, subtracted the lower limit, and got the correct answer. Problem 51 from section 8.2. In class we mentioned that anytime you had an inverse trig function, you would let that be u because the derivative of the arc cosine is an algebraic expression, and we don't have a simple integral. So we're going to let u equal the arc cosine of x, and we're going to let dv, pardon me, yes, we're going to let dv equal dx. So when we take the derivative of this, we have to go to chapter 5 because I don't remember it always. I think it's negative as far as the expression for the derivative of the inverse cosine. So it's going to be negative 1 over the square root of 1 minus x squared, the whole thing times dx. And v is just going to be equal to x. So the integration by parts formula is the integral of u dv is u times v minus the integral of v du. So substituting in u and v, and I went ahead and put them in the correct order here. So we get x times the arc cosine of x. And we have minus the integral of v, which is x, divided by the square root of 1 minus x squared, the whole thing times dx. And I'm going to do this as an indefinite integral, and then when I get to the point where I have it integrated, I will then put the limits of integration in. So we need to do this integral, and we did something like it in class, so I'm not going to go through the details since that's already done, but you're going to have to, I'm going to write them in here, we're going to need a 2 to get, when we take the derivative of this will be u, the derivative of that will be negative 2x dx. So I need a 2, so I need to divide by 2, and then need a negative sign to go along with it, so I'll make that positive. So this part is du, this part is u, so when you integrate it, we're going to get 1/2, and the integral of that will be u to the positive 1/2 divided by 1/2. So what we'll have is we'll have the square root of 1 minus x squared divided by 1/2. Okay, so the 1/2 comes from when we integrate this. This is to the 1/2 power. So you take the new exponent, divide by, you take it to the new exponent, and then you divide by the new exponent. So 2 times 1/2 is 1. So we end up with the arc, x times the arc cosine of x plus the square root of 1 minus x squared. And let's put these on 2 pages now. So now we can evaluate it at the 2 limits, the upper and lower limit. So what we will have is we'll put a bracket, x times the arc cosine of x plus the square root of 1 minus x squared, evaluated between the limits of the integration, which we go back to the beginning of the problem, are 0 and 1/2. I don't know why I put, it's like I'm putting pi there, but it's not time to do that yet. Okay, so at the upper limit, so we're going to do this at the upper limit and subtract from the lower limit. So we have 1/2 times the arc cosine of 1/2 minus 0 times the arc cosine of 0. Then we have plus the square root of 1 minus 1/2 quantity squared minus the square root of 1 minus 0 squared. Well, the angle whose cosine is 1/2, it's going to either be pi over 6 or pi over 3. And if you think about a unit circle, and cosine is the x value. So when x is 1/2, that's halfway between the origin and the outside of the circle. So that's going to come up to here, and that's going to intersect it at pi over 3. So we're going to get 2 times pi over 3. This is going to be 0. Here we'll get 1 minus a quarter, which will be 3/4, and we'll square that, which will be 9/16. Is that right? 1 minus a quarter is 3/4. Squared is going to be 9/16, and we subtract off the square root of 1, which is 1. So we get pi over 6. And so we have 9/16 minus 16/16, which would be negative 7/16. So let's look at the answer. Oh, yeah, I messed up there. Okay, sorry. This part's wrong. Because I didn't take I need to take the square root, so it's going to be the square root of 3 divided by 4, which is the same as the square root of 3 over 2. So that's plus, and we subtract 1. So that's the final answer. And you can get a decimal number if you want to, and the decimal number is going to be equal to 0.658. Okay, we're on problem 55, section 8.2. So we look at this and we say, there's a natural logarithm. I bet that's probably a good thing to choose for you. So let's do that. And therefore, what's left over is going to be dv. So we get x squared dx, which we can integrate pretty easily. So du is equal to 1 over x dx. And v is going to be equal to x cubed over 3. Integration by parts says that the integral of u dv is uv minus the integral of v du. So with what we have in the problem, and again I'm going to change the order of these just because I can do that now. Hopefully by this point we are getting to a point where we're more comfortable, and that's just so that this is last. It's just, it doesn't confuse. The confusing thing is the x cubed in there or not, and if you have it in this order, then it doesn't get confusing. So then you have the integral of v times du. So we're going to simplify the integral before we do this, and I'm going to factor out a negative 1/3, and so we have x cubed divided by x, which is x squared. So the first part stays the same, and we integrate that, so we get our constant times the integral of x squared, which is x cubed over 3 again, plus our arbitrary constant c. So we end up with x cubed over 3 times the natural log of x minus 1/9 x cubed. And let's go one more step here. Let's factor out a 9, x cubed over 9. And what that'll leave is 3 times the natural log of x minus 1. And I forgot that I was doing a definite integral, so I could sort of leave my arbitrary constant off at this point, and then I will now put down the limits of integration. And the limits were from 1 to 2, so let's go down here. And we'll rewrite it on the
we have
next
two
page.
curves. We have a straight line and we have a parabola.
Cubed over 9
And the straight line is
times 3 times the natural log of
the,
x minus 1.
parabola.
Evaluated
So our
between x equals 1
function
and
we will
x
subtract
equals
is
2.
f of x, and the one we'll subtract it from is
So
g
at
of
the
x.
upper limit, we're going to have
Now the question is, where are those points of
cubed
intersection? We have 2 points of
over
intersection,
9
so you can kind of read it off the
minus,
graph, but it doesn't seem
and
like...
yeah, let's just do the upper limit and then subtract the lower limit. So at the upper limit, we get 2 cubed over 9, 3 times the natural log of 2 minus 1. And at the lower limit, we have, so we subtracted off at the lower limit, 1 cubed over 9 times 3 times the natural log of 1 minus 1. That whole thing closed. Well, the natural log of 1 is 0. So we'll end up with 8/9 times 3 times the natural log of 2. So that's the first term. Now I'm going to multiply this out, and I'll get negative 8/9. And here I will have negative times a positive, so I'll get plus, and I have plus 1/9. So if I do this, I'll get 8/9. Actually, no, I got the 3. I got to cancel that out. So I'll have 8/3 times the natural log of 2. And if you have negative 8/9 plus 1/9, will give you negative 7/9. And this is problem number 55. So let's see what the book says. 8/3 natural log of 2 minus 7/9. Okay, so that's correct. And if you plug it into your calculator, you'll get 1.071. Okay, so this is the last problem in section 8.2. And for the same reasons as before, we're going to use the arc sine, any inverse trig functions. We are going to, the arc secant, we're going to make equal to u, and therefore dv is going to be what's left over, which is x dx. Okay, so we take the derivative of u, and the secant, arc secant, that means we have to go back to chapter 5 again, because I don't remember it. And the arc secant is going to be equal to, okay, so we have, it says u prime, but the argument is x, so it's just 1 divided by the absolute value of u, which is x, and times the square root of x squared minus 1 dx. So that's the derivative of the arc secant. And if we integrate x dx, we get x squared. That's it. Oh, x squared over 2. Okay, so hopefully what's going to work out is that when we multiply this times that, we get something that we can integrate, which we do. So we say the integral of u dv is u v minus the integral of v du. Again, I'm going to change the order of multiplication here just to save one step. And again, we're doing the indefinite integral until we get to the end. So just make sure, hold on just a second, don't go anywhere. Okay, just want to make sure I knew where the answer was, so when I get to that part. And then we have negative the integral of v, which is x squared over 2, times du, which is 1 over x times the square root of x squared minus 1 dx. And at first that looks pretty complicated, but when we simplify that, and I'm going to add another page, and we're going to just do that second integral by itself, what we'll get, the second integral, let's go ahead and leave the negative sign there. So you get x squared divided by x. So we get x divided by 2 times the square root of x squared minus 1, the whole thing times dx. So hopefully what you can see, let's go ahead and factor out a negative or 2. So this is 1/2. We may have to put it back in later, but it's just to start off with. It's just a little simpler to look at without the 2 in there. So in this case, let's use w as our substitution variable. So we're going to let w equal x squared minus 1, which is determine the square root. So we take the differential, and we would get 2x dx. So you can see we have x dx, so we need 2x dx, so we're going to multiply by 2 here, and we're going to divide by 2 outside. So we'll end up with negative 1/4 times the integral of 2x dx, which is du, divided by the square root of x squared minus 1, which is equal to u. I put u. I should be putting w here. Hold on. Okay, so dw. And so we get negative 1/4 the square root of w divided by 1/2. We've done that integral so many times that I'm just not going to do it again. Okay, so we have 4 times 1/2, which is 2. So we're going to end up with negative 1/2 times the square root of w, which is x squared minus 1. So that is the integral, the second integral. And make sure we have everything straight. So we got negative, which was originally there, and I didn't factor any negative. So that's exactly what I want. So we're going to go back over here and plug it in. So we have x squared over 2, the arc secant of x minus 1/2 square root x squared minus 1. Now I'm going to add a new page in. Oops, sorry. Add a new page in. And now we're going to take this and we're going to make it into a definite integral. So all we do is we just rewrite the integral. And I left the arbitrary constant off because I didn't need it once I made this into a definite integral. So we go from x equals 2 to x equals 4. And so we evaluate it at the upper and lower limits. So let's just do that. So we'll get 2 squared, we'll get 4 squared over 2 times the arc secant of 4 minus 2 squared over 2 times the arc secant of 2. So that's this part. And then we'll get negative 1/2 times the square root of 4 squared minus 1. And we'll subtract off the square root of 2 squared minus 1. And so, it's going to have a fair number of terms if we don't put it into decimal form. So let's just go ahead and go as far as we can. So we'll have 4 squared divided by 2, which is 8. So we get 8 times the arc secant of 4. And the angle whose secant is 2 is the same as the angle whose cosine is 1/2, which is, we just did that a second ago, it was pi over 3. So we'll get 4 divided by 2, so we'll get 2 times pi over 3. And then we'll have minus, here we get the square root of 15, so we'll have the square root of 15 divided by 2. And then we have a negative times a negative is a positive, so we'll get positive. We get 4 squared minus 1, which is 3, so we get the square root of 3 over 2. And one last step, and we could then just plug this stuff into the calculator. So we'll get negative 2 pi over 3 minus the square root of 15 over 2 plus the square root of 3 over 2. I'm just checking all my numbers here. And if you plug those in, one thing is to remember is the arc secant of 4 is the same as the arc cosine of 1/4. And if you plug those in there, so you can use your calculator to do that, the inverse cosine of 1/4 times 8, etc., 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 and you plug the numbers in, you'll get 7.380 as far as the integral is concerned.